Hi, welcome to MDIS Virtual Fair. I'm Meng, and today I will be doing a presentation on wireless technology. Okay, let's start with looking at the outline for today's presentation. Firstly, we will look at the history of wireless technology, the benefits of wireless technology, followed by time and frequency domain and concept, and after which we will discuss about amplitude and frequency modulation, followed by Wi-Fi network and future developments. In the history of wireless technology, as early as 1880, Hertz discovered electromagnetic waves. And in 1898, the first commercial radio data service was developed and followed by the first mobile radio in 1921. And after 20 years later, the first mobile telephone service in St. Louis by AT&T are developed. And 30 years later, we have the first human cellular phone service in Chicago by AT&T as well. And 1971, we have the first wireless data network Aloha at Uni of Hawaii, followed by wireless net product at AT&T as well in the early 1990s. So we can clearly see the development of wireless technology over the past 100 years. And in the latest, we have 1997, the first wireless LAN standard IEEE 802.11 at 2 megabits per second was rolled out. That was the first communication standard. Okay. So before we move on, let's take a look at the comparison between wired and wireless communication. For wired deployment, each cable is a different channel. So each cable is able to support a different channel frequency, and the signal attenuation is low with little interference or no interference because each cable is protected by its own cladding devices. So the electromagnetic waves is not able to attenuate clearly in the cladding. So most of it will be contained within the cable, the cable itself. And in the good old days, it will be copper cables. And if you look at wireless technology, one cable can be shared by many sources. And it's also subjected to high signal attenuation, high interference, such as co-channel interference, adjacent channel interference, and noise as well. This is because the electromagnetic waves are propagating in the air, and there are other electromagnetic waves being used for other commercial products or industry research as well. And that is why the signals are subjected to high attenuation and high interference from other sources and devices. However, the benefits of wireless technology still outweigh the shortfalls. For example, there's not a need to lay abundant cables like in the early 1990s. A lot of cables have to be laid because each cable only contains one channel. So without the laying of abundant cables, it helps to reduce manufacturing complexity and cost. Thus, it's more reliable due to less physical connections involved, and therefore, it's easier to maintain and modify after production. So on the whole, it is of much more benefits than a wire deployment. Next, let's take a look at some facts. All right, in the worldwide mobile subscribers, you can see from 2007 and compared to 2000, we have nearly more than 1 to 3 billion of subscribers. That is a lot as compared to fixed line subscriber. You see, 1.35 billion subscriber versus 1.2 billion fixed line at the end of 2003. So it's clearly evidence that mobile subscribers are getting more and more congested as compared to fixed line subscriber. And in 2020, 6.1 billion smartphones are estimated across the whole world, and it's far exceeding the number of fixed line subscription. Before we move on to look at the various concepts or techniques involving time frequency modulation, let's take a look at the applications at the various frequency bands. So in this figure, you can see the commercially exploited bands of the radio frequency spectrum. From the left, we have the maritime radio navigation that is operating at a very low frequency VLF, and the frequency range is from 3 kHz to 30 kHz. For this frequency band, majority of the application lies in maritime radio and navigation. And then we move up to another frequency band, LF, low frequency, operating between 30 kHz to 300 kHz. So at low F frequency band is also mainly used for maritime radio and navigation. So later part, we will take a look at the relationship between frequency and wavelength and how it applies to all these different applications. So moving up the band, we have MF, which is medium wave or medium frequency. It's operating from 300 kHz to 3 MHz. And it's mainly used for AM radio, aviation radio, and navigation as well. So we can see at this frequency band, right, we have the incorporation of amplitude modulation, AM, and some of our radio channels are basically using AM. So from 300 kHz to 3 MHz, we see the involvement of AM channels into our world. And next, we move on to HF, which is high frequency, and in short, it's also called shortwave frequency. And it's mainly used for shortwave radio, operating from 3 MHz to 30 MHz. So we are now moving into the megahertz range. And moving up the channel, we have VHF, very high frequency, operating from 30 MHz to 300 MHz. And it's mainly used for VHF television, FM radio, which is the channel that we are using now for our digital home devices. So at this point, we can see the involvement of FM channel into our applications, and AM radio is still in the MF medium frequency. So it's clearly shown that the frequency gap between AM and FM is almost 30 MHz. That's to distinguish between the AM modulation and FM modulation such that there will not be cross-channel interference. And we move on to UHF, television, mobile phones, GPS, Wi-Fi, and 4G, etc. And the frequency band is UHF, ultra high frequency, with a frequency range from 300 MHz to 3 GHz. And if you look at one of the applications here, GPS and Wi-Fi, these are the more commonly used applications these days. And in particularly, in Wi-Fi, we are operating at 2.4 GHz and 5 GHz. All right. So at this UHF band, we have 2.4 GHz because the frequency range is from 300 to 3 GHz. And if you are talking about 5 GHz Wi-Fi, we will move up to one more level, which is SHF, super high frequency, with a frequency range from 3 GHz to 30 GHz. And at this frequency band, it's mainly used for satellite communications and Wi-Fi. So for Wi-Fi application, it basically occupies two frequency bands, UHF and SHF. And lastly, we have the EHF, extremely high frequency, with a frequency range from 30 GHz to 300 GHz. So it's mainly used for radio astronomy, satellite communication. So at one glance, we can see the frequency range from the left to the right, from the very low frequency band to the extremely high frequency band, all right, from 3 kHz all the way right through to 300 GHz. So can one of you audience here can explain what's the main difference between the application from the left to the right? So that means from maritime radio navigation on the left under VLF, very low frequency band, all the way to satellite communications under extremely high frequency. So first thing first that comes to our mind basically will be the relationship between wavelength, that means the repetition of every signal, all right, and the relationship between wavelength with the frequency. So it will lead us to the universal equation C equals to F lambda. C is the speed of light, F is the operating frequency of the signal, and lambda is the wavelength of the signal. So if C, which is the speed of light, equals to 3 times 10 to the power of 8 meters per second, equals to the operating frequency. In this case, if we choose 3 kHz or we choose 300 gigahertz, all right, multiplied by lambda. So if we make lambda the subject of the equation, so lambda equals to c over f, that means it's equals to speed of light 3 times 10 to the power of 8 meters per second over the operating frequency. Let it be 3 kilohertz, that means 3000, or the extremely high frequency 300 gigahertz, which is 300 times 10 to the power of 9. So we can clearly see the wavelength will start from maybe just a few meters to a few thousand kilometers. So meaning that the operating frequency has a direct impact on the wavelength, and the wavelength will determine the amount of coverage provided by the operating frequency. And that is the reason why for maritime radio navigation, they tend to be operating at the lower frequency BLF, because for the distance between the boats, the ships from, for example, South China Sea to Pacific Oceans, we're talking about hundreds, maybe thousands of kilometers. And that's why the signal that is operating needs to be able to cover a large coverage, provide a large coverage. All right, as compared to, for example, Wi-Fi, which is operating at 2.4 gigahertz or 5 gigahertz. So Wi-Fi, we are talking about gigahertz, but for maritime applications, we are talking about only kilohertz. So from 1000 hertz to gigahertz, which is 10 to the power of 9, we are talking about 1 million times different. So meaning that the differences in the wavelength, that means the coverage provided will also be different in terms of million times as well. So why is Wi-Fi operating at higher frequency? For Wi-Fi, we're talking about local coverage, maybe within a shopping mall, within a school compound, campus, or within a commercial buildings. So it's strictly constrained by the walls as well, right? So we're not talking about large coverage in the whole entire town, in the whole entire city. So that's why Wi-Fi operating frequency is around megahertz or kilohertz. In this case, we're talking about 2.4, so it will be gigahertz. All right, so the wavelength will be smaller because the coverage does not need to be as far wide as the maritime navigation. So this figure, all right, clearly shows the applications from very low frequency to extremely high frequency, right through from maritime applications to satellite communication. So with that, let's move on with the next slide. So before we move on with the transmission technique used for signal, let's take a look at the fundamentals of all propagation, which is time and frequency domain. So in time domain signals, it basically just provides the information regarding the value of any functions or signal at any instance. They basically do not convey the information as to the rate at which the signal is varying. And that is why we need to represent the signal in another domain. So frequency domain arises. And how to relate, what's the relationship between frequency and time? I believe some of us will know that frequency equals to 1 over t, which is 1 over the period, or vice versa, t equals to 1 over the operating frequency. So if the frequency is high, the wavelength, the time period will be small. And if the frequency is low, the time frequency will be high. So electromagnetic signal is used as a means to transmit information. And EM is a function of time, but it can be expressed also as a function of frequency. So later part, I will show how to convert between time and frequency domain. So EM signal, all right, is the signal that comprises of components of frequencies. However, the frequency domain view the signal, all right, is more important than time domain. Okay, so in this slide, we can see a pure sine wave on the left-hand side. All right, so what is wavelength? Basically, wavelength, as mentioned earlier, all right, c equals to f lambda that we mentioned in the earlier slide. Okay, wavelength is the distance occupied by a single cycle of the signal, or the distance between 2 points of corresponding phase of 2 consecutive cycles. So if you look at the bottom left figures, all right, it's in terms of time domain. It's voltage against time, so voltage versus millisecond, and the wavelength, as mentioned, is a repetition of every repeated cycle. So in this case, the wavelength occupies a time duration of 10 milliseconds. All right, and if you want to convert this time duration to frequency, we look at the bottom right-hand figures. By using f equals to 1 over lambda or f equals to 1 over t, we can easily calculate the frequency or the operating frequency of this sine wave. So given a wavelength duration of 10 milliseconds, so we use f equals to 1 over lambda, which is f equals to 1 over, yes, that's right, 10 milliseconds is also 0.01. So 1 over 0.01 will give us 100 Hertz. So when it's converted to frequency domain, all right, it's being represented as one single spike carrier, as we can see here, represented by the blue arrow, which is operating at 100 Hertz. So next question is, what is the meaning of 100 Hertz? What's the meaning of 10 milliseconds? We already know that 10 milliseconds in this case is the time duration of one wavelength, one repeated cycle. But how about 100 Hertz? What's the meaning of 100 Hertz? Okay, so 100 Hertz in this case, what? We have to understand what's the meaning of Hertz. Basically, Hertz is the frequency or is the rate at which the cycle will be repeated within 1 second. So in this case, we're talking about 100 Hertz. So meaning that there are 100 seconds, 100 cycles per second. So if you're talking about 1 kilohertz, there will be 1000 repeated cycles per second. So that is at the lower session. So if you're talking about, for example, 1 megahertz or 1 kilohertz, for example, if you're talking about satellite communication, we're talking about 300 kilohertz. So 300 kilohertz or 300 gigahertz, that is 300 times 10 to the power of 9 cycles per second. So that is almost 1 billion times more than what we have here. All right. So we can clearly see the relationship between frequency and wavelength. They can be 1,000 times, 1 million times, or even 1 billion times difference according to the operating frequency. Okay. So in this figure, we have demonstrated the conversion between time domain and frequency domain. So let's move on with the next slide. What would be a good representation of frequency domain? Yes, I believe some of you or most of us here will have seen this radio receiver in our house, right? Used by our parents, used by our grandparents. This is a very good representation or demonstration of the frequency domain. You can clearly see in this figure, all right? We have the top section, the top band, which is 88 megahertz, right through to 108 megahertz. And the bottom section, we have AM, the lower frequency, from 530 kilohertz to 1700 kilohertz. So the bottom sections, the user is able to tune the knob between 530 kilohertz to 1700 kilohertz. On the top, the user is able to tune from 88 megahertz to 108 megahertz. If you notice, these are all the, yes, that's right, frequency used by the local radio channels. For example, we have class 95, 90.5, power 98, all right, also 98.7 megahertz. You can clearly see this actually is the frequency range of the local radio stations, right? So before we move on with explanation discussion on amplitude modulation, frequency modulation, let's take a look at one line quoted from the movie I'm Legend. So how many of you have watched this movie I'm Legend? I think it was released in the year 2007. This movie is about virus. Of course, we are not talking about virus for this presentation. We're talking about transmission wireless technology. So in this movie, Will Smith mentioned, all right, I'm broadcasting on all AM frequencies. I will be at the South Street Seaports every day at midday. So my question for everyone is, in the movie, why did Will Smith broadcast his message using AM frequencies and not FM frequencies? All right, when we tune into our local radios every day, class 95, power 98, all right, love 91.3, we're talking about FM radio channels, all right, and it's all between 90 to 100 megahertz. But why in this movie, Will Smith specifically mentioned that he's broadcasting on AM channels and not FM? Since if you are tuning into radio, that means the radio channels are able to be covered on a wide area. But in this case, Will Smith, instead of using FM, is using AM. Any guess here? Why in the movie, Will Smith is broadcasting on AM channels in the movie I'm Legend? Any guess? Anyone? That's right. Okay, as mentioned earlier, at lower frequency, the AM channels, all right, at a smaller frequency band, the wavelength will be higher. So with a higher wavelength or longer wavelength, the signal is able to provide a larger coverage. Whereas in the AFM channel, they're operating at megahertz, so the wavelength will be much more smaller, maybe lesser by 1,000 to 10,000 times, and that's why the coverage by FM is smaller. Right? So the primary purpose of modulation in the communication system is to generate a modulated signal suited to the characteristic of transmission channel, and that is the reason why Will Smith is transmitting on modulation channel, either FM or AM, and in this case, he's using AM. So modulation is needed in the transmission systems to transfer the message into the available high frequency radio channel. So in the movie, he's using AM because he's able to provide larger coverage, and he's trying to reach out all the other survivors in the area, and that's why he's using AM. So we know now why AM is preferred for larger surface coverage as compared to FM. FM is more for smaller area localization, for example, TV channels, radio channels as well. Okay, so on the opposite, we have AM operating at a lower kilohertz, and that's why maritime applications are using all the lower frequencies, because they can provide direct communication between the boats, between the ships across the oceans. So that is one big important relationship between frequency and wavelength. So let's move back to modulation. So now we know the importance of modulation. Basically is to provide the modulation of signals such that it's able to propagate in the free space. So let's start off with AM modulation, amplitude modulation. So AM is a modulation technique where the amplitude of a carrier varies depending on the information signal. And the AM radio broadcast signals using lower carrier frequencies, and we have seen this in the earlier slide. So this helps them to travel long distance. So there is another strong fact to show why the movie is using AM, because it's able to travel longer distance due to lower frequencies. So AM signals can be able to bounce off the ionosphere, and when they bounce off the ionosphere, they can reach other parts of the world or the Earth. And that is the reason why they are able to travel longer distance or provide larger coverage as well. So now we can clearly see the advantage of AM, which is its ability to travel further down the propagation path, and it's also able to bounce off the ionosphere and travel back onto the Earth's surface. So with that, we can take a look at frequency modulation. So frequency modulation, as implied by the name, frequency, so it's dealing with the hertz. That's right. It's a technique used to encode data on an alternating digital or analog signal. And the method includes varying the frequency of the carrier wave on which the useful information is imposed or impressed upon. As you can see in this figure, when we are dealing with FM frequency modulation, the carrier frequency basically varies. You can see the wavelength of the signal at the center of the figure. All right, sometimes it's more concentrated together, sometimes it's further apart. So when the signal is spaced further apart, meaning that the wavelength, the period is, that's right, bigger. So when the wavelength is bigger, the operating frequency is smaller. So at the smaller wavelength, lambda, so f equals to 1 over t, when t reduces, frequency will be higher. That's right. So when you see that the repeated wavelengths are more congested together, that means they are operating at higher frequency. Whereas if you see the wavelength is spaced further apart, that means they're operating at smaller frequency, and thus they're able to provide bigger coverage. So this is a very distinguishable differences between AM and FM. So now let's take a look at the overall differences between AM and FM. For FM, now we move on with AM first. The first successful audio transmission was carried out in the mid-1870s. So it's clearly seen that in the early 80s, all right, transmission was already into its research sections by humans. And the first radio wave is called a carrier wave, and the frequency and phase remains the same. However, is subjected to poor sound quality and can transmit longer, but it can transmit longer distance, as already proven in the earlier slide, right? And the frequency range for AM radio waves starts from, yes, 535 to about 1700 kilohertz. However, it is more affected by the presence of noise. On the other hand, for FM signal is developed in the early 1990s by Edwin Armstrong in the United States. And the radio wave is called a carrier wave, but the amplitude and phase remains the same. So only the frequency varies. The amplitude and phase remains the same. It's able to provide higher bandwidth with better sound quality. And also, at the same time, the frequency range starts from 88 megahertz. So it starts from the megahertz range right through to 108 megahertz. All right, so this basically evidence that it's in the higher band and it is less affected by the presence of noise. So at one glance, we can see the main difference between AM and FM. Apparently, is the frequency range. For AM, is operating in the kilohertz range from 500 to 1700 kilohertz as compared to FM, which is 88 to 100 megahertz. And the next distinguishable differences is the, yes, AM is more affected by noise as compared to FM, which is less affected by noise. So in this table, we have a clear understanding of the differences between AM and FM. So I hope you're enjoying the talk so far. So let's move on with the next type of modulation. Digital modulation. This modulation scheme is important in the sense that it is related to an application that we are using every single day. So what is digital modulation? Digital modulation is a generic name for modulation techniques that use discrete signals to modulate a carrier wave. All right, in comparison, frequency modulation and amplitude modulations are analog techniques. And the three main types of digital modulations are frequency shift, phase shift, and amplitude shift. And the all-time common or frequently used wireless services Wi-Fi uses this digital modulation, which allows the transfer of a digital bit stream over analog channel at high frequency. So this enables us to transmit signals generated in a digital circuit across a physical medium. And this because the digital signals can be handled with higher security and digital signals are readily and widely available. So now we know that Wi-Fi services basically uses digital modulation to transfer the data, all right, from one point to another. Wi-Fi. So I believe all of us know this icon by now. All right, it's shown in the school, campus, a shopping mall, or in commercial buildings, offices as well. So Wi-Fi is a wireless network technology that allows devices such as laptops, desktops, mobile devices, and other equipments to interface with the internet and use radio waves to provide wireless high-speed internet and network connections. So what are the operating frequencies again, everyone? That's right, 2.4 gigahertz and 5 gigahertz. So before we move on with other discussions, let's take a look at the Wi-Fi background. So in the early 19s, 802.11 development was started by IEEE, and the aim was purely to develop a standards for medium access control MAC and physical layer 5. And in 1997, the first version of 802.11 standard was ratified. So it took about 7 years for the standard to be developed. And the first version developed, all right, was able to deliver 1 megabytes per second and also 2 megabytes per second. It was considered abundant in the good old days in the early 1990s. And in the late 1990s, the 20.11a and 2.11b amendments were released. Of course, improvements definitely are made on the megabits per second. So it was improved to 5.5 megabits per second and 11 megabits per second at 2.4 gigahertz. And also, security features are introduced, such as WEP, the wire equivalence privacy. And with that, we have also 5 gigahertz operating with orthogonal frequency multiplexing modulation at 54 megabits. So it's clearly evidence that between 2.4 and 5 gigahertz, the 5 gigahertz Wi-Fi is able to accommodate bigger bandwidth such that users are able to upload and download files at a much shorter time duration. So that was made available or made ready with the 5 gigahertz operating at octagonal frequency division. And in the early 20s, the FCC approved the use of octagon frequency multiplexing at 2.4 gigahertz as well, and also in 2003 at 54 megabits as well. So in the late 20s, 802.11n amendments were ratified. So this heavily relied on the multiple input, multiple output technology, which helps to improve the bandwidth. And they both uses 2.4 gigahertz and 5 gigahertz at the same time. And other improvements as well, including the bandwidth, right through to 600 megabits per second. And also the introduction of Bluetooth in the year of 2009. And we also have a Bluetooth high-speed channel as well. So with that, we move on with the more improved versions under 2.11 AC, which is still under development during that period of time. And now we are looking at Wi-Fi 6. Okay, so in the later part, we will take a look at the improvement under Wi-Fi 6 version. So Wi-Fi benefits include mobility, compatibility, the high-speed data, of course, and not forgetting security, because we are not keen to have data being transmitted without any security features to protect our files. And Wi-Fi can be easily installed, all right, using APs, all right, so easy installations, all right, at low cost. So if you look at the structures, infrastructures, buildings around us, all right, we are able to see all the access points APs on the ceilings of the rooms or the offices, all right, that helps to transmit the Wi-Fi signals to all the users. So Wi-Fi advancements, Wi-Fi uses electromagnetic waves to communicate data. There are two main frequencies that we already know. At 2.4 gigahertz, which is 802.11b, and 5 gigahertz, 802.11a. So for so many years, 2.4 gigahertz was a popular choice for Wi-Fi users. All right, and then in 2003, all right, mankind prefers to have faster speeds and larger coverage. So they come up with the 11G standards. All right, and routers were getting better too with higher power and further coverage than ever. And Wi-Fi was beginning to catch up with computing speed of the wire connections. So in the early 1990s or in the early 20s, wire connections or LAN connections is still faster as compared to wireless technology. But with the advancement of technology over the years, especially over the past 10 years, we can see the increment in the transmission band, all right, from gigahertz to, that's right, okay, from the lower end, kilohertz to gigahertz, all right, and bandwidth from 100 or maybe 10 megabytes per second to 100 megabits per second. And in the late 20s, we saw the final version of 2.11n, which was even faster and more reliable than its predecessor. And this increase in efficiency is attributed to the AS-MIMO, all right? Multiple input, multiple outputs. So multiple source and multiple destinations data are integrated together. And that's why it's able to support larger bandwidth. Okay, so this allows for significant increase in data without the need for higher bandwidth or transmit power. And the 2.4 gigahertz extended range means that there's an increasing number of devices from baby monitors to Bluetooth using the same frequency, and also causing it to be overcrowded and slower. And that is why developers roll out the 5 gigahertz services to share the heavy traffic at 2.4 gigahertz. So from 2012 onwards, the 11 AC standards aim to make 5 gigahertz range better. You have 4 times the speed. Take note, 4 times the speed, that's a lot more. All right, and the greater width and the ability to support more antennas, meaning data could be sent more quickly. And 2012 also see the birth of the beamforming concept, which allows signals to focus and concentrate on data transmission so that the data reaches the target devices faster. All right, so instead of using omnidirectional, all right, omnidirectional coverage, which spread to 360-degree areas, we are talking about directional coverage, which is a direct path between the transmitting and the receiving antenna. So for infrastructure, we have 4 types of infrastructure. Let's take a look at the first type, basic service sets. So for basic service sets, okay, we have a set of stations controlled by a single coordination function as shown in the figure on the right, and typically use an access point. As mentioned, access point, you can see the access point being installed on the ceilings of rooms, offices, shopping malls, etc. And all mobile stations must be accessible by the access point of the infrastructure. And in this network, stations must associate with the access point in order to get access to network services. All right. And also independent base service sets, that is a direct connection, all right, between the mobile clients as shown on the figure on the right as well. So without access point, we are talking about a connection between mobile clients, for example, by means of using Bluetooth. All right, you can send packets of files between devices, between handphones, between tablets, between the iPads as well. Right. The next system or infrastructure, yes, distribution systems. Looking on the figure on the right, you can see a main systems to connect 2 or more BSS. All right, the basic systems together, and they are typically wired internet, followed by extended service sets, ESS. So a set of more of all these basic service interconnected by a distribution services or distributed systems. So we can see a combination of both BSS, independent BSS, or also a standard BSS being connected to the distribution systems together. Okay. Security. We have looked at the infrastructure. So now let's look at security. Security is utmost important. All right. If everyone has read the news yesterday, late yesterday or early this morning, all right, a lot of prominent figures, their accounts have been hacked. All right, including Donald Trump, Obama, a lot of their personal accounts have been hacked and important information are leaked out. So we can see how important security is. So likewise for Wi-Fi connections, we need to have a reasonable security features to ensure that the packets of files that we send are being transmitted safely to the end user. So the use of Wi-Fi today is summed up nicely by Rethink Wireless. The Wi-Fi performance continues to improve and is one of the most ubiquitous wireless communications technologies in use today. It's easy to install, simple to use, and economic too. And the access points are easily set up at home, in public spots, in shopping mall, in offices, in all areas, giving convenient internet access to everyone, all right, from laptops to smartphones, etc. And encryption technologies make Wi-Fi secure, keeping out the unwanted intruders from this wireless communication. So Wi-Fi security, all right, Wi-Fi is potentially more vulnerable to attack than wired networks because their presence in the air and anyone with antennas is able to tap on all these wireless signals. So to connect a Wi-Fi network, a Wi-Fi typically needs the network name, the SSID, the password. The user password is used to encrypt the Wi-Fi packets to unblock these undesirables. Wi-Fi protected access is intended to protect information moving across the Wi-Fi networks and also includes versions for personal and enterprise networks. So Wi-Fi needs to be integrated with a high security features to ensure that packets of data are sent across safely and accurately. So developing security features of WPA have included stronger protections and new security practices. So let's take a look at the 4 types of protections. Firstly, we have the wired equivalent privacies. Wired equivalent privacies. This encryption standard was the original encryption standard for wireless. And the security issues are known since 2001. Okay? It can be cracked in less than 1 minute. And then we have the improved version WPA, wireless protected access. It's a software or firmware that is made improved over WEP. WPA is a trimmed down version of this 11 series, and it uses the TK for encryption, and some routers also support the AES. Next, we have the wireless protected access WPA2, so this is an enhanced version. Okay, basically it provides stronger data protection and network access control. It provides enterprise and consumers Wi-Fi users with a high standards of assurance that only authorized users can access their wireless networks. And WPA2 is therefore preferred over the earlier version WPA. And we can also have the wireline authentication and privacy infrastructure, WAPI. Right, this is mainly used or defined by the Chinese government and is supported by cell phone sold in China. So you can see different markets, different countries have their own encryption, their own security features as well. So now let's move on with coverage. We have mentioned about security. All right. So security is important as well as coverage because we want to ensure that there are sufficient number of users being able to be covered under the access point area. So Wi-Fi networks have a range that's limited by the frequency, transmission power, antenna types, the location they are in, and the environment. And a typical wireless router in an indoor point-to-point arrangement using the 11N series standard and antennas may also have a range of 50 meters, and that's good enough to cover an entire shopping mall, perhaps, right? Antennas can be made to improve on router's performance, such as positioning a router in an open space so that there is very little constraint due to the presence of walls. All right, and you can also change your wireless channel, update the router's firmware, update the wireless adapters driver, and also replace your router's antenna. All right, you can talk about omnidirectional antennas or directional antennas. It's all subjected to the applications that you're talking about, whether you want to be deploying the router in an enclosed area or you want to have direct line of sight. Okay. And also a wireless repeater such that the wireless signal is being enhanced or boosted up. So future developments, we are looking at Wi-Fi 6, the next generation of Wi-Fi. All right, after Wi-Fi 5. You still do the same basic thing, connect you to the internet, just that, okay, it isn't talking about just top speed or boosting the speed for individual devices. Wi-Fi 6 is also about improving the network when a bunch of devices are connected. So we are talking about accuracy of the connections, all right, and stability of the connections, all right, apart from, of course, the speed at which the data is being transferred. So Wi-Fi 6 can handle more devices at one time, okay, so you can support more users, is able to keep speed and latency more consistent even under heavy load. That means stability has increased. And since most people keep their routers for years, so it may be time to upgrade the phones or computers multiple times before getting a new router. All right, or it's best to get a router ready for the future for Wi-Fi 6, right? So the next big thing will be Wi-Fi 6 or maybe Wi-Fi 7 in the pipeline as well. So with that, if you have any further inquiries, all right, feel free to contact our support, okay, as shown in this slide. Mr. Zhang, Mr. Darren, and Mr. Bill, all right. The numbers and the emails are as shown here, all right. So with that, we will welcome the next speaker shortly at 3 p.m. Thank you.